come with me to this side here of the booth to actually take a look at the first application we displayed here on the left. This is the application brought here and implemented by the team of the University of Southern California. Just kind of cover all the corners as this is here. And this application is targeting polishing and sanding tasks. So Ryan, maybe fill us in with some details about these tasks and where you would typically use these applications.
Thank you, Daniel. We're creating a solution for automated surface finishing applications like sanding, polishing, cleaning, all these different tasks. We all know that 3D printing has become very popular. All the big aerospace companies are adopting 3D printing in their small volume production. But what people don't talk about is the third side of additive manufacturing. A metal part like this takes about a day to actually print, and then it takes about 7 days of surface finishing and post-processing, which is done manually, to actually be able to use the part. And that's where our solution comes into the picture, to cover the last mile of manufacturing process. And it's a collaborative system between human and robot.
Yeah, thanks so much. So how does it actually work? How can you get into the process as a worker, and how do you generate the trajectories of the part?
Exactly. So actually the system starts by importing a CAD model into as input in our system. You can define the region that you want to finish and give it to the robots. And after that, using our planning algorithms, two robots determine how they should collaborate and generate the path so that they can finish all the region on the part. The more challenging aspect is that how do you ensure you get the desired surface finish? How do you make sure you achieve the right surface roughness? We use our machine learning algorithm to determine the right settings of the operation. For example, what should be the right force, the right stiffness of the arm, right tool speed, etc. Because all these parameters vary for every part and every tool to get the best performance.
Yeah, very interesting. But still, this is also a human collaboration or human-robot interaction scenario. So how do I actually get into contact with the robot system? Or how can actually the robot system tell me what I need to do?
Exactly. So the human in our system, the human is always in the loop and making high-level decisions. And whenever there is some attention needed by the robot from the human, they send text message or some notification in their smartwatch to call the human and help them out. But for example, the assistants might be changing a tool, flipping the part, or handling some contingency that may arise in the system. We also use an augmented reality system, which is actually on charge at the moment, to guide the human operator to place the part on the right location or calibrate the system.
Yeah, so very good. Thanks for the explanations. Maybe just to sum it up, Ron, give us some ideas. Where are you going? What are you going to do next? And where this system can be used in future?
Yeah, so our application has potential in all, starting from small machine shops all the way to big aerospace corporations. We're actually collaborating with NASA. We're planning to take this robot in space, where they can 3D print a metal part, polish it, and then immediately start using it.
Yeah, very good. Thanks a lot.
Thank you, Daniel.
We can also move on to the right here, to the next application. Where we are
space отправиться.
Here the setting is different. Here we are assisting the human operator in carrying large parts and types like this. Tito, maybe some details about the application and about the use.
We are presenting here a human robot collaboration station where human is assisted by a robot as an electronics inside the aircraft stage. The system is made of KUKA
the operator just do the sun freely, or is there any set trajectory where you can also assist the operator?
So we are implementing some virtual features in order to guide the human operators through the assembly execution. And during the first motion, you can see a tunnel in which the human is guided through. And here we have also some virtual features demonstrating the human motion. So the robot motion while guided by the human.
Very nice. So what is actually your strategy to proceed here? How do you bring this interesting application to the shop?
So we are involved in the Eureka project that is for Airbus. We are bringing this technology to their facilities, and we just need to certify the software and go through some risk analysis.
Yeah, thank you very much. We will move on here to the next application in the middle. So this application is also based on a human collaboration scenario, but here we are exploring the capabilities of new systems of making these human collaboration scenarios more efficient. So Roman, give us some hints what are the typical challenges in realistic human-robot collaboration scenarios are.
Thank you. Hello everybody. So what you can see here is a standard industrial application, and our goal is to get the robots out of the fences to make safe and efficient human-robot collaboration. KUKA developed the LBR EVA, which has no sharp edges and which is sensitive to detect collisions, but the robot needs tools and moving objects. These tools and objects are often not safe for human-robot collaboration. We were trying to solve this problem.
Yeah, speaking about solutions, so maybe you can then explain what the solution actually is and how does it work to provide this safe and efficient human-robot collaboration.
Yeah, as you can see here, we always inflate an airbag before we start a motion so that we are intrinsically safe when we move the robot. When we then stop the robot, we can pull everything back so that we can free the tool and the object so that we are able to manipulate the robot again.
Yeah, very interesting. So now we have an additional system on the robot which makes it more efficient and safe. So maybe you could also say some words about how I can interact with the complete system or composed of the robot and the airbag.
Yes, of course. We integrated sensors to the airbag so that we were able to interact with the airbag and of course check all the time the status, interact and detect collisions. So now I interact with the airbag by squeezing it, and of course when the robot moves I do not have clamp between two objects, I just have clamp between the soft airbag.
Yeah, very nice. So maybe just as a final hint, what is the rationale of your application?
Yeah, we want to make human-robot collaboration safe and efficient for the future. Thank you.
Yeah, and as I may also mention, they not only want to do it, they also were able to actually win the KUKA Innovation Award, and this application here makes our winner. So, thank you a lot, but there's a lot to see and more interesting things to explore here on the booth. So now we are seeing the two robots set up by EPFL from Switzerland, and they actually have built and implemented this scenario for two robot arm handover situations. So Sina, maybe give us some information about the typical challenges in these scenarios.
So in this scenario, we have two-arm collaboration with the human. The first and most important thing is when we are talking about the human next to the robot is the safety. We propose the control architecture to make sure that any interaction between the human and the robot is going to be safe, and that will be happen to the human.
Yeah, that's good. So now we are safe in our application. But you also mentioned there are several challenges. So what would be the next challenge you are actually targeting in your solution?
So the next challenge is going to be the robot safety. As we are talking about the multi-arm manipulation, the system should be safe, which means that there should not be any collision while the motion is going to be executed. Right now, Nadia is moving the arms next to each other, and you can see that even though the robots are complementary to the human, but they are also safe. And moving one of the arms toward the other arm makes the other arm move away to make sure that they are safe. So as you can see, Nadia is moving one of the arms toward the other arm, and the other arm is moving away to make sure that no collision right now our experiment is the handover of the big object to the robot. When the big object is going towards the robot, as you can see, the robot has started to coordinate with each other and with the object such that they can reach to the object simultaneously and they can grab it when it is out.
Yeah, very good, thank you. But maybe there's some final sentence to say. What is the key highlight in your application here?
So we have three levels of coordination here. We coordinate the arms with the human to make sure that nothing happens to the human and the human robot will not make mistakes. We coordinate the arms with each other to make sure that nothing will happen while the arms are moving next to each other. And we coordinate the arms with the real object to make sure that we can accomplish the task.
Yeah, thank you very much. And we will move on to the final application, more to the right here of the booth. Which is also extremely interesting. So if I may. So this application is also a two-robot application. But now here you see the robot manipulator on the left side, and on the right side you will see a flying system. So Antonio, maybe you can tell us why you actually use this two-robot system and what the task is here.
Hello everybody, first of all. So what we want to do here is to push forward the capability of ground manipulators and allow the manipulation of long or large objects from one end. So this manipulation is impossible because of the high torque that are needed for ground manipulators, and the system we present is a system with two robots, a flying robot and a ground robot, that allows to achieve this task.
Yeah, very nice. So I see the two robot systems are quite different. So maybe you can fill us in how you actually leverage the individual capabilities of these two robot systems for realizing your application.
Yes. First of all, perhaps I want to mention that in the current moment, the aerial robot is operated through the haptic interface that you see there. So there is a human operator that does a shared control with the system. And then as soon as the robot will pick up or grasp the object, the operator will be out of the loop and the system will be completely automatic, and it will share the load using force control from both sides.
Yeah, very interesting. Speaking of control and the operator, can you say some words on the control system which you use to coordinate these two systems here?
Yes, the control system is based on force control, and the challenging part here is the aerial part. Because the aerial part, it's very hard to estimate forces with using actuators like propellers, because you have aerodynamics involved. And so we really had a big challenge in developing a control method, and which also has an onboard estimator to achieve.
Yeah, very interesting. So maybe you can just say something about the key highlight here in the system and where you can actually use it in future.
The key highlight, you have seen it right now. So the robustness of the system, the cable was stuck, and thanks to this force control, the system is not just doing position control and trying to do in any case, but it's really measuring this force and having a certain compliance to the external world.
Yeah, thank you very much, and also thank you all for your kind attention here for our application and our finalists. So I wish you a